Welcome to our latest video on the topic of redox titrations. This is the third video in the series and it has a title Using Redox Titrations in the Analysis of Copper 2 Ions, and this video is suitable for A-level students. By the end of this video lesson, you should be able to describe and explain the colour changes associated with the addition of an iodide solution to a solution of copper 2 ions. You should also understand how a redox titration with sodium thiosulfate can be then carried out to determine the moles and mass of copper 2 ions. Now, in our previous videos on redox titrations, we've discussed the fact that these titrations involve both reduction and oxidation reactions, and in the two previous videos we've discussed titrations involving manganate 7 and dichromate 6. And these two chemicals are oxidizing agents. They will cause another substance to lose electrons, and in the process they're themselves reduced. Now, in this video you're going to come across thiosulfate being used as a reducing agent. A reducing agent is a substance that causes another to gain electrons. Now, redox titrations can be used to determine the purity of substances. For example, they're regularly used to analyze metals and their compounds. Now, in this video, we're going to focus on how redox titrations can be used in the analysis of copper 2+ ions. And in these redox titrations, we're going to be using sodium thiosulfate as a reducing agent. So to test your understanding of what we've covered in previous video lessons, here's a quick practice question. So read for the question, pause the video, have a go at the first part of this question, and then we'll go for the answers, and then we'll look at the second part of the question, which involves a titration calculation. So this question says 0.180 grams of an alloy containing iron was converted to a solution of iron 2 ions by dissolving in acid, and then the solution required 26.5 centimeters cubed of a solution containing dichromate ions of concentration 0.0167 for complete oxidation to iron 3 ions. So the first part of this question gives you the iron half equation for the oxidation of iron 2. And it asks you to write the iron electron half equation for the reduction of Cr2O7 2-. So to do this, I'm going to write down the Cr2O7 2- ion, and I'm going to draw an arrow to show it change into Cr3+ and H2O. Now I have to learn that, I have to remember that it changes to Cr3+. And when dichromate oxidizes any substance, it is itself reduced, so that's why I'm adding H+ ions and electrons on the left hand side. Now to balance the equation, I've got Cr2O7 2-, so I've got 2 chromiums on the left, so that's why I put a 2 in front of the Cr3+. Because I've got 7 oxygens, I put a 7 in front of the H2O. That gives me 14 hydrogens, so I put a 14 in front of the H+. And I get the charges balanced by putting a 6 in front of the electrons. So there it would be Cr2O7 2- plus 14H plus 6 electrons goes to 2 Cr3 plus 7 H2O, and the charges are balanced because on the left hand side we've got 2- and 14 pluses plus 6 electrons, which puts that to 6+ on the left, and on the right hand side we've got 2 Cr3+ ions, which is also 6+ charge on the right hand side. So here's the second part of this practice question. Read for the question, pause the video, have a go at it, and then we'll go for the answers. So to carry out this calculation, we first have to write the overall equation for the reaction of dichromate and iron 2+. So we've already written the half equation for the reduction of dichromate, and the half equation for the oxidation of iron 2+ was written in the first part of the question. Now, to combine the half equations to write an overall equation, I need the same number of electrons in both equations. That's why we're multiplying the bottom equation here by 6. Once I've done that, all I have to do is add the two equations together and the electrons will cancel out. So the overall equation is Cr2O72- plus 14H plus 6Fe2 plus goes to 2Cr3 plus 7H2O plus 6Fe3 plus. Now I'll need this overall equation to be able to attempt the titration calculation, because I need to know the ratio of dichromate to Fe2 plus. And I can see from the overall equation it's a 1:6 ratio. So the first thing I do to answer this question is I work out the moles of dichromate, and to do this I do concentration over 1,000 times volume. Now the concentration of dichromate is 0.0167. I get this from the question. I divide it by 1,000 and I times it by the titration value, which is 26.5. Now the value for the moles of Cr2O72- comes out to be 4.4255 times 10 to the minus 4. So now that we know the moles of dichromate, to work out the moles of Fe2 plus, I simply just use the overall equation. And as it's a 1:6 ratio, I just times the moles of dichromate by 6. So it would be 6 times 4.4255 times 10 to the minus 4. So that would give me a moles of Fe2 plus equal to 2.6553 times 10 to the minus 3. So now that we know the moles of Fe2 plus, we can work out the mass of iron present, because the mass of iron will simply be the moles times the AR value of iron. So this will be 2.6553 times 10 to the minus 3 times 55.8, which is the AR value of iron. So if we do 2.6553 times 10 to the minus 3 and we times it by 55.8, we will have a mass of iron, and this mass of iron will be 0.148 grams. Now the question is asking us to work out the percentage of iron present in the alloy. Now we know there's a mass of 0.148 grams, and we know that the alloy had a mass of 0.180. So all we need to do is express this as a percentage. So it's 0.148 divided by 0.180 times 100, which comes to be 82.3%. So this is a 3-mark question. There's 1 mark for getting the moles of dichromate correct, 1 mark for getting the moles of Fe2 plus correct, and 1 mark for the final answer. Now in this video we're going to look at how we use redox titrations in the analysis of copper 2 ions. Now determining the moles and mass of copper 2 ions in solution is not a straightforward process. However, we can carry this out indirectly by reacting a solution of copper 2 ions with a soluble iodide, such as potassium iodide. Now if you add an iodide solution to blue copper 2 solution, the result is the formation of a cloudy brown solution. And this is because the copper 2 ions react with the iodide ions to form a brown solution of iodine and are reduced to form copper 1 plus in a precipitate of copper 1 iodide. Now the following equation describes the chemical reaction taking place. Copper 2 plus ions would react with iodide ions to form copper 1 iodide and iodine, and it's the copper 1 iodide that is the precipitate, and the iodine is a brown solution. So that's why you end up with a cloudy brown solution, because you have this precipitate of copper 1 iodide and your brown iodine solution. So the equation would be 2 Cu2 plus ions react with 4 iodide I minus ions to form 2 Cui plus I2. And we can carry out a titration with sodium thiosulfate to determine the moles of iodine formed in this reaction. And from this, we can calculate the moles and mass of copper 2 present in the solution. So this is what we mean by carrying out an experiment indirectly to measure the moles and mass of copper. We react the copper 2 plus with an iodide solution to form copper, 1 iodide and iodine, and then we can titrate the mixture with sodium thiosulfate, a reducing agent, to find the moles of iodine, and from this we can work out the moles of copper and the mass of copper present. So this slide shows a picture of the cloudy brown solution that would form if we reacted a solution of copper 2 plus ions with a solution of iodide ions such as potassium iodide, and we would form this copper 1 iodide and iodine, and that's the cloudy brown solution. Now, aqueous iodine is produced when these iodide ions are oxidized by the addition of copper 2 plus, which acts as an oxidizing agent here, and the iodine can then be titrated against sodium thiosulfate solution using starch as an indicator. Now, when you add starch to your flask and it contains iodine, your solution will go blue-black in colour. And during this titration, the blue-black colour will be lost because the iodine is being converted to iodide in the following reaction. So we have two thiosulfate ions, S2O32-, reacting with I2, iodine, to form S4O62- and two iodide ions. Now at the end point, your solution will be colourless because there'll be no iodine present. Now remember, starch turns a blue-black colour in the presence of iodine. When iodine is titrated against thiosulfate, it's converted into iodide. When there's no iodine left, the blue-black colour is lost and you have a colourless solution. So to determine the endpoint, we just need the volume of thiosulfate needed to turn the solution colourless from blue-black. Now if you look at the two equations on this slide, you can see that 2 moles of copper 2 plus form 1 mole of iodine. And 1 mole of iodine reacts with 2 moles of thiosulfate, S2O32-. So therefore, the moles of S2O32- must be equal to the moles of copper 2 plus. And this is how we use this redox titration to work out the moles of copper 2 plus and ultimately the mass of copper present. So I'm now going to prove to you that the moles of thiosulfate equals the moles of copper. So imagine that I had 0.2 moles of Cu2 plus in my flask and I reacted it with iodide solution. Because there's a 2-to-1 ratio of copper 2 plus and iodine being formed, I would have 0.1 moles of iodine being formed. And because there's a similar 2-to-1 ratio of thiosulfate to iodine, this would react with 0.2 moles of thiosulfate. So you can see that the moles of copper is equal to the moles of thiosulfate. So in this redox titration, all you need to do to work out the moles of copper 2 plus is just calculate the moles of thiosulfate that is reacting in the titration. So we're now going to see a short video clip of this experiment, and this comes courtesy of the C.R. Harrison YouTube channel, which is definitely worth checking out on YouTube as it contains lots of really good experimental footage. So in the flask we have a solution of copper 2 plus ions, so we have a blue solution, and if potassium iodide is added to the flask and we swirl the flask, and we're going to add some water here to ensure that there's no potassium iodide on the walls of the flask, you can see that a cloudy brown solution forms. Now if we were to add starch to this and add thiosulfate, we wouldn't see the colour change. So what we tend to do is we tend to add the thiosulfate until the cloudy brown solution goes a straw-coloured yellow solution, and then we add the starch and your solution will go blue-black, and then we continue adding the thiosulfate until the blue-black colour disappears at the end point. And when the blue-black colour disappears, we have our end point and we know the volume of thiosulfate needed in the reaction. So now let's test your understanding of this with some practice questions. Read through the question, pause the video, have a go at it, and then we'll go through the calculation step by step. So now let's go through the calculation step by step. So the first thing I need to do is write down my equation that shows the reaction that's taken place between copper 2 plus and iodide ions. So it'll be 2Cu2 plus 4I minus forms 2Cui plus I2. And the thiosulfate will react with iodine as follows in the titration. So we'd have 2S2O3 2 minus plus I2 forms S4O6 2 minus plus 2I minus. Now from these equations you can see that 2 moles of copper 2 plus ions will produce 1 mole of iodine. So there's a 2-to-1 ratio here. And the iodine that's formed in this reaction of copper 2 plus and iodide ions will react with thiosulfate in a titration in a 1-to-2 ratio. So 1 mole of iodine, I2, will react with 2 moles of thiosulfate, S2O3 2 minus. Now because of this means that the moles of copper 2 plus ions is equal to the moles of thiosulfate. So in this calculation, the first thing we need to do is work out the moles of thiosulfate that was needed in the titration. Now if we know the moles of thiosulfate needed in the titration, we know the moles of copper 2 plus, because the moles of thiosulfate is equal to the moles of copper 2 plus. So to work out the moles of thiosulfate, we do concentration over 1,000 times volume, and that would be 0.2 over 1,000 times 21.10, and that would give us a number of moles of 4.22 times 10 to the minus 3. Now the moles of thiosulfate is 4.22 times 10 to the minus 3, so therefore the moles of copper 2 plus in 25 centimeters cubed would also be 4.22 times 10 to the minus 3. So 4.22 times 10 to the minus 3 would be the moles of copper 2 plus in 25 centimeters cubed of solution, but our original solution was 250 centimeters cubed. And in 250 centimeters cubed, the original solution, it must be 4.22 times 10 to the minus 2, because we have to times the moles of copper 2 plus in 25 by 10 to find the moles of copper 2 plus in 250. Now the next step is to work out the mass of copper in 250 centimeters cubed. So to do this we need the moles of copper in 250 centimeters cubed, and we need to times it by the AR of copper, which is 63.5. Now if we do this, we get a mass of copper equal to 2.68 grams. Now in the experiment, a brass screw 3.75 grams in mass was dissolved in the beaker of concentrated nitric acid. So to work out the percentage mass, we need to do 2.68 divided by 3.75, which was the mass of the brass screw, and times it by 100. And if we do this, we'll get our percentage of copper, and this comes out to be 71.47%. So here's our second practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 2 says a sample of Bordeaux mixture was analysed to determine its copper content. Firstly, it was reacted with excess potassium iodide, and the equation is shown for you here. And the iodine produced was then titrated against sodium thiosulfate solution, and once again the equation has been given to you. And the first part of the question says name the indicator used for the titration and state the colour change at the end point. Well, this is a 2-mark question, so if you name the indicator correctly as starch, you get 1 mark, and the colour change would be, it would go from blue-black to colourless. So if you said the indicator changes from blue-black to colourless, you get the 2nd mark. So now let's go through the calculation part of this question, part 2. So in this question, it says that there's 12.25 centimeters cubed of sodium thiosulfate solution with concentration 0.100 mole per decimeter cubed that reacted with the liberated iodine, and it's asking you to calculate the mass of copper in the sample and hence the percentage of copper by mass. So we have to remember that 2 moles of CO2 plus ions form 1 mole of iodine, and 1 mole of iodine will react with 2 moles of thiosulfate during the titration, and therefore the moles of copper 2 plus must be equal to the moles of thiosulfate. So my first step here is to work out the moles of thiosulfate. So just to emphasize that the key point in this calculation is that the moles of copper 2 plus is equal to the moles of thiosulfate. So in any of these calculations, you should be looking to work out the moles of thiosulfate from the titration data first. So thiosulfate has a concentration of 0.100 moles per decimeter cubed, and a volume of 12.25 centimeters cubed was needed in the titration. So the moles of thiosulfate is concentration over 1,000 times volume, so the concentration is 0.100, and if I divide this by 1,000 and I times it by my volume, which is 12.25 centimeters cubed, I will be able to work out the moles of thiosulfate. And the moles of thiosulfate is 1.225 times 10 to the minus 3. Now, the moles of Cu2 plus present in my flask will also be equal to 1.225 times 10 to the minus 3, because the moles of copper 2 plus is equal to the moles of thiosulfate. Now the question is asking me to work out the percentage mass of copper. So I need to work out the mass of copper present in my flask. Now if I know the moles of Cu2 plus, to convert this to mass, I just simply times by the AR value of copper, which is 63.5, and this will give me a mass for copper present in the flask. So it would be 1.225 times 10 to the minus 3 times 63.5, and that gives me a mass in grams of 0.0778 grams. Now to work out the percentage of copper present in my sample, all I do is take the mass of copper that I've just worked out, 0.0778, and I divide this by the mass of the sample, which was 31.2. So I'm going to do 0.0778 divided by 31.2. I'm going to times it by 100, and this will give me the percentage mass of copper, and it's going to be very small. It's going to come out to be 0.249%. So this is a 3-mark question. You get 1 mark for getting the correct number of moles of thiosulfate, 1 mark for getting the mass of copper correct and 1 mark for the percentage correct. So here's our final practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go through the calculation step by step. So once again in this question, you're asked to work out the percentage by mass of copper. So we have to remember that the moles of copper 2+ is equal to the moles of thiosulfate, and we've seen that in all the previous calculations. So to work out the moles of thiosulfate, I need to use the following equation. I need to remember that moles of thiosulfate is equal to concentration over 1,000 times volume. So the concentration of sodium thiosulfate here is 0.196 moles per decimeter cubed. So I'm going to divide that by 1,000 and I'm going to times it by the volume. And the volume given to you in the question is 20.3 centimeters cubed. So to work out the moles of thiosulfate, I have 0.196 over 1,000 times 20.3, and this comes out to be 3.9788 times 10 to the minus 3. Now the moles of thiosulfate is equal to the moles of Cu2+. So the moles of Cu2+ in 25 centimeters cubed will be equal to 3.9788 times 10 to the minus 3. Now, because we need to work out the percentage mass of copper in the crystals, we need to work out the moles of Cu2+ in 250 centimeters cubed, because that was our original solution. So to do this, we just need to times the moles in 25 by 10, and this will be 3.9788 times 10 to the minus 2. And that will be our moles in 250 centimeters cubed. Now, if I'm going to work out the percentage by mass, I need to work out the mass of copper in 250 centimeters cubed. So this will simply be 3.9788 times 10 to the minus 2 times by the AR value for copper, which you remember is 63.5. So if I do 3.9788 times 10 to the minus 2 times 63.5, I will get a value for the mass of copper present in my 250 centimeters cubed flask. And this will come out to be 2.53 grams. Now the question is asking you to work out the percentage of copper in the copper 2 sulfate crystals. So you need to know the mass of the copper 2 sulfate crystals, which was 10 grams. So therefore, to work out the percentage mass, I just do 2.53 divided by 10 times 100, which comes out to be 25.3%. So you get 1 mark here for getting the moles of thiosulfate correct. You get 1 mark here for getting the moles of copper 2+ in 250 centimeters cubed correct. You get 1 mark for getting the mass of copper present in 250 centimeters cubed correct, and 1 mark for the final percentage. So that concludes this video lesson. So after watching this video, you should now be able to describe and explain the colour changes associated with the addition of iodide solution to a solution of copper 2 ions. And also you should be able to understand how a redox titration with sodium thiosulfate can then be carried out to determine the moles and mass of copper 2 ions present. So that concludes this video lesson. So please check out our YouTube channel, Dr. Rowe Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.